We're going to take a few moments to talk about bases and their properties and how to construct them. Intuitively, a basis is the most economical way to span a subspace. Like we said earlier, if we have a basis for a given subspace in R to the n, then any vector y in this subspace can be uniquely written as a linear combination of vectors in our basis, x1 through xk. The unique coefficients in this linear combination are sometimes called the coordinates of y in this basis. The first fundamental result of linear algebra is that every subspace in R to the n actually has a basis. This is not an entirely trivial thing to see. To try to get at why it's true, let's make two more statements about subspaces and their bases. Suppose we have a subspace S. Then any set of vectors, x1 through xk, that spans S and is minimal, in the sense that if we remove any one of the x's, they no longer span. This set must be a basis. Suppose that S is a subspace of R to the n. And suppose first that x1 through xk are k vectors in S that are a maximal linearly independent set. This means they're linearly independent as a set, and if we take any other vector y in S and add it to the set, then y and the x's are not linearly independent. The result is that the x's form a basis for S. Similarly, if we have a minimal spanning set in S, this also forms a basis. This means that if we take k vectors, x1 through xk, that span S, and are such that if we removed any one of the x's, the remaining ones would not span S, then the x's must form a basis. Now, I haven't told you what k is, and I haven't said that k is the same in one case or the other. But let me try to give you an idea of why these statements are true. And by doing so, I'll give you an idea of why the fundamental theorem is true, that any subspace has a basis. To give you an idea of why these statements are true, and then why the fundamental theorem is true, that any subspace in R to the n has a basis, I need to use a basic lemma. The lemma is any linearly independent set of vectors in S can be extended to a basis by adding things to it. Moreover, the extension is finite. I can add a finite number of things and get a basis. And similarly, if I have any set of vectors that spans S, I can reduce it in a finite number of steps to a basis. This basically proves any subspace of R to the n has a basis. So let's think about how this works. So let's see why these two simple statements are true. Suppose I have a space S, a subspace of R to the n, and a maximal independent set. This must be a basis for the following reason. If it's maximally independent, it means that if I take any other vector in S and add it to the set, this vector must be a linear combination of the previous elements. It can't be linearly independent by definition. But then that means that my set of k vectors, x1 through xk, actually span the set X. I've just shown that anything in S has to be written as a linear combination of x1 through xk. Therefore, x1 through xk form a basis. Similarly, there's the second statement that a minimal spanning set has to be a basis. And so in this case, I need to show that a minimal spanning set consists of linearly independent vectors. Suppose that there's a relation among them. Suppose that some linear combination of them is equal to 0, or alternatively, suppose that one element in the set can be written as a linear combination of the others. Well, if that were true, I could easily remove that element and find a smaller set that still spans S. Therefore, a minimal spanning set is automatically linearly independent and also has to be a basis. This set must be a basis. Again, let me say that again. So, suppose we have a subspace. Suppose we have a subspace S. And suppose that we have a maximal, God damn it. Suppose we have, So this means that x1 through xk are linearly independent. Holy fuck. Have I gotten this all backwards? Sorry, I want a minimal spanning set, and I want a maximal independent set. I have no idea how I just said that, but I'm just going to do it again. Sorry. And if we add any other vector to the x's, to this set of k vectors, it can't... I'm sorry, this is just... No. Take 8. Suppose that I have k independent vectors in a subspace S, and I want to extend it to a basis. Well, let me add to it another vector that's not in S. It's in the complement of S, so it's somewhere in R to the n. It's not in S. Then it actually has to be linearly independent with... Oh, that's a horrible thing to do. God, that's not what I want to do at all. So, what's the point? I want to start with an independent set and extend it to a maximal independent set. But the thing about subspaces of R to the n is entirely idiotic. You should just be looking at R to the n itself. There's no reason to work with subspaces.
Yeah.
Right, good.